Hi everyone, am I audible? Anyone just can you confirm? So you can type in the chat box, right? You don't need to start your mic. So let me do one thing. Um, am I audible? Please confirm by typing in the chat box. Okay, yeah, great. So I hope I'm audible and let's start today's session. So welcome to this NPTEL tutorial sessions on linear algebra through geometry, right? So this is a tutorial session. I am Rupesh Kumar and I'll be hosting these sessions every Friday 6 to 8, right? Everyone, let's start with some basic set of instructions, set of rules for these sessions. So the first thing, all of these sessions are recorded, so you will get a video recording of these sessions, right? So don't worry about if you miss these sessions. You will be getting a pre-recorded versions of these tutorial sessions. In this session, what I will be doing is start with some basic problems that I have with me, and I will solve those problems for you guys, right? And during the session, you can ask any doubts you have regarding to the problems that I'm discussing in these sessions. And how will you be communicating with me is only through the chat box. So you don't need to unmute yourself. You have to remain muted for throughout the session, and you will not be allowed to speak through your mics, right? The only way you are communicating with me is through the chat box. Is this clear? And make sure these sessions will be uploaded online, so please don't stay away from any nuisance stuff, right? So yeah, and the questions that I will be covering in these sessions will be from the topics from the week topics covered in the week just before this session. So this is the first session, so I'll be covering the topics covered in the first week, right? And at any instant you face that my voice is not coming or my screen is not visible, or if there are some any technical glitches, then you just have to type in the chat box as soon as possible, right? And yeah, if you have any doubts in the questions, you just have to ask me during when I'm solving that problem at that instant itself. You don't just don't wait for the end of the session. Just ask your questions in the chat box at that instant itself. Fine. And other than that, if you have any queries about the logistics of the NPTEL course, how the examination will take place, what topics will be covered, or any other things, I won't be able to help you in those topics with those topics. I'm just here to help you out, help you to solve few practice problems on the topics that you have studied in the NPTEL course. Fine. Anyone do you have any other doubts? Please type in the chat box. So I can't explain anything related to the exam pattern of the NPTEL team. Fine. So let's for a few more minutes. So wait for a few more minutes so that everyone can join and then we will start the session, right? So, hi everyone, welcome again. So, so let's start today's session. Fine. I hope I'm audible and uh, let me start the screen recording, right? Hello. Yeah. Mhm. Yes. Fine. So let's start with the first problem. Let me open another chat box. Yeah, fine. So is my screen visible, everyone? So is my screen shared with you guys? Is it visible? Anyone, please confirm. Great. So let's start with the first problem. So which of the following represents a homogeneous system of linear equations in two unknowns, right? So, um, so these are four figures, right? The coordinate axes are x1 and x2, and you are given graphs for graphs of four such system, and the equations corresponding to red and blue lines consider the system of linear equations. And the question is, which one of the following represent a homogeneous system of linear equations in two unknowns, right? Mm. Anyone? Do you have any answers for this problem? So let me open up the chat box. Yeah, right. Option two, cause they intersect in zero. Option B, second graph V. Yes, because of the matrix y equals to mx. So fine, your answers seem correct, right? Option two, the definition of a homogeneous system of equations is that the solution must contain the system of equations must have the trivial solution as their solution, and the trivial solution is you set all the equation where coefficients to zero for all the bases. Fine, everyone. Anyone, do you have any doubts in this? Just type in the chat box. Fine. So everyone, please make sure your videos are also uh, turned off, right? So let me just open it up on my screen sharing. Okay. This is here. Okay, fine. Let me. Yeah, fine. So we are done with the first problem. So yeah, which of the following represents a homogeneous system of equations? The solution is option B. So this is the right answer. Fine. So all the a system of equation is said to be homogeneous system of equations if you can write the system as, let's say you have two bases x1 and x2, right? So you can say, let's say we have a set of bases alpha of 1 x1 plus alpha 2 x2 equals to 0. And then you can all write beta 1 x x2 equals to 0. So for these systems of equations, you can always say that the solutions are x1 equals to 0, x2 equals to 0. So this trivial solution always satisfies these systems of equations. So that's why these are, so these kind of equations are known as uh, uh, homogeneous systems of equations. Fine, everyone? Yeah. So this is the first problem that we discussed. And if you look at geometrically, this means for any system of equation, if you have some solution, if you have two linear equations and you want to find out the solution of these two linear equations, what you do, you always plot these linear equations, the lines corresponding to these linear equations on the coordinate axis, and find the point of intersection. And that point of intersection essentially corresponds to a solution. So for option B, you can see that the point at which these intersect is the point 0, right? These two linear equations intersect at the origin. That's why x1 equals to 0 and y1 equals to 0 equals to 0. X1 equals to 0 and x2 equals to 0 is a solution. That's why this is a homogeneous system of equations, right? So if you look geometrically for homogeneous systems of equations, they always intersect at the origin. Fine, everyone. Do you have any doubts? Another way to say this is these systems of equations can be written as Ax equals to 0, where X is your set of unknowns, right? And A is the matrix containing basis of these equations. Basically, A is the matrix that can be written like this. So A contains x1, 0, 0, x2. And then the matrix vector X can be written as alpha. So Ax equals to 0, right? Alpha 1, alpha 2, and then alpha 1 x1 plus alpha 2 x2 equals to 0, and beta 1, beta 2. So these kind of systems can be, these are basically, then you want to solve for x1 and x2. So yeah, Right. Okay, yeah. So I have done some mistake here. Let me just correct this. Fine. So you can always say that if you want to see how it can be written as a in a system of matrices, you can always say this is alpha 1, alpha 2, beta 1, beta 2. So this is the matrix A multiplied by the matrix X containing the unknowns, which are x1 and x2, and you want this to be 0, right? So from this matrix vector product, you can always get this system of linear equations, and you can always solve them to find that x1 and x2 are 0, which is a solution to the system of equations. And geometrically, you can always see that they intersect at the origin. Fine, everyone. I hope this is clear, and I have explained it well. So should we move on to the next question, everyone? Fine. I think no one has any doubts. So let's move on to the next question. Which one of the following represents a system of linear equations in two unknowns with unique solution? Fine. So you have uh, so the question is we want to find which one of the following represents a system of linear equations in two unknowns with unique solution. So you have to pay attention to the question. It says unique solution and it has to have two unknowns, right? So you can always draw two axes for these two unknowns on the Cartesian plane. So let's say the unknowns are x1 and x2 in the coordinate axis, and you want to find if it has a unique solution, right? So for this you have to go back to into the theory, like how what are these linear equations and what corresponds to the solution of these linear equations, right? So a system of linear equations can have number one, unique solution, right? Unique solution, one solution, right? Then infinite many solutions, many solutions, and lastly no solution, right? So when you will come across these situations for unique solution, if you look geometrically how it will look like. So let's say we have set of unknowns represented over the axis x1 and x2. Then for unique solution, your both linear equations, both the lines will intersect at a single point. For example, this example. In this example, you will find a unique solution. So this corresponds to the case one, right? So this corresponds to case one. Fine. So let's look on to the second situation where you might have infinite many solutions. In these situations, you will find that um, so these two lines basically are overlapping, right? So basically, this kind of situation will arrive when there are infinite many solutions. So for any pair of x1 and x2, the pair will satisfy uh, all the values of x1 and x2 will satisfy the condition that these points lie on the both the lines, right? Let's move on to the third case, which is no solution. So in this case, you will see that. So let's say these are the axes x1 and x2. So in the third case, you will see that these lines representing the system of equation are parallel. So there is no solution for this case, right? So these are the three cases that you might arrive. And then if you have unique solutions or infinite many solutions, you can always find if it's satisfied, it has trivial solution. So let's look at our solution of our possible options. So option one, you can always see there is a unique point here, right? This is a unique solution. So this is correct, right? Then second graph, you can see it has a unique solution at x1 equals to 0 and x2 equals to 0. So this is also correct. Fine. So this is, yeah. Let's move on to the third point, third graph. Here again, you can see one unique point where both of these are, both equations, linear equations are intersecting. So you get a unique solution. And in the last case also, you get the same scenario. You get some unique solution, right? So all of these are correct solutions for this problem. Fine, everyone. Do you have any doubt? Anyone, if you have any doubts, please type in the chat box right now. Anyone, do you have any doubts? So no one has any doubts. Fine. So should we proceed? Am I audible? Great, great. So let's start. Let's proceed. Fine. I hope my text is also visible clearly. Fine. Someone is asking where will we get the recordings? So the recordings will be shared by the NPTEL team. Any other doubts? I don't think so. Fine. Fine. So let's start with the third problem. Which one of following is not true about the following system of linear equations? Fine. So you have x1 plus x2 equals to a and 2x1 plus 2x2 equals to b. The question is, has unique solution if b equals to 2a, has infinite many solution. The options are basically has a unique solution if b equals to a, 2a, has infinite many solutions if b equals to 2a, has no solution if b not equals to 2a, and the corresponding homogeneous system of equations is consistent. Fine. So why consistency? So let's again go back. What is the meaning of consistency? The meaning of consistency is that it contains at least one solution. Fine, everyone. System of equations is said to be consistent. Linear equation is said to be consistent if there are at least one solution to the to the given system of equations. Fine. I hope you are familiar with these uh, definitions, right? So anyone, do you have any solutions for this problem? So let's see how we can solve this problem, right? So let's try to solve it geometrically, right? So again, we can define the basis x1, the coordinates x1 and x2. And now the first equation says x1 plus x2 equals to a, right? So you can always say let's try to solve these systems of equations. So x1 equals to a minus x2 again. And then you can say 2x1 plus 2x2 equals to b. So you can substitute the value of x1 from equation 1 into equation 2, right? Substitute the value of x1 from equation 1 to equation 2. You can say 2, so substitute value of x1 into equation 2, right? You can say 2 into a minus x2 plus 2x2 equals to b, right? So this is what you have to solve. So let's try to solve this. So you have to find the value of a. So the equation now you get is 2 into a minus x2 plus 2x2 equals to b. This is the one single equation containing one variable, which is x2, right? X2 is unknown. Others are, let's assume that they are known. So how to solve this problem? So just move out all the coefficients of x2, right? So take out x2, the coefficient would be 2 minus x2, right? Okay, so acha, fine. So you can see the system is basically dependent, right? So it's saying x2, the coefficient becomes x2, 2 minus 2 plus 2a equals to b, right? So you're saying x1 plus x2 equals to a, x1 plus x2 equals to 2b. So these sessions will be held every week. Right. Again, so you can always say if now the condition is if a equals to 2b, what happens, right? So when a equals to 2b, you get a single equation, that is x1 plus x2 equals to some constant which is a, right? Or which is equals to 2b. Fine. So now there are infinite many possible values of So there are infinite many possible values of x1 and x2 that corresponds to this equation, right? So let's say I choose a equals to some value, let's say 0. So so la yeah. So how which values so what will it will say x1 equals to minus x2, right? So you can also always plot this x1 y x1 equals to x1. Yeah, right. This is x1, this is x2. Mm, X. So it passes through the origin, fine, and y equals to minus x, fine. So the slope is -1. So the line looks like this, right? So if and then you can simply choose the value of a, and the line can just move in this direction, right? These are all possible lines that's so I think option B is correct, right? Everyone, do you have any doubts? Some of you guys have said option A is correct. Can anyone explain why you are saying this? Okay, right, right. Fine. So, okay, so let's pay attention to this. This says which of this is not true, right? So basically, these are all infinite possible values for this problem. So yeah, there was my mistake. I read something wrong in this problem, right? So it says which is not true, right? So what is true? It is true that you get a linear equation, a single equation containing two unknowns, x1 and x2, and infinite many possible combinations of x1 and x2 can be formed to get an to solve the that satisfies this condition, and that can be seen geometrically if you plot this over the coordinates for x1 and x2. You can see this is a line that can pass that is parallel to the line x1 equals to minus x2. So all of these lines satisfy this single criteria based depending on the value of a. And if I choose a to be if I choose a to be 0, then you get this line that passes through the origin, right? If you choose a to be 0, then you will get this line. Fine. So yeah, this is the solution for a equals to 0. So it has infinite many solutions if b equals to ta, right? So option it does not have unique solution. So option A is not true. So the correct answer is option A. Fine. So it has infinite many solutions, which is true. Has no solution if b not equals to 2l. So let's check for this. If b is not equals to 2a, then what you get? Then you sorry, then you get. So let's try to see through this. Fine. As no b not equals to 2a, then you will have x1 plus x2 equals to a, and x1 plus x2 equals to b by 2, right? So this is what can we say about this system of equations? Mm. Again, if a is 0 and b is 0, then you don't uh then again so but it satisfies the criteria that b equals to 2a, right? Mm. So let's see. If you choose a equals to 1, let's say, and b uh, equals to 2a, so let's choose b also equals to 1. Right. So if you choose a equals to 1 and b equals to 1, then this will be half, right? So you will get this line and these two separate lines. So there is no unique solution. So there is no solution, right? So option C has to be correct. Fine, everyone. So if b is not equals to 2a, if b is not equals to 2a, so then you can see, right? So let's say we choose a equals to 1 and b equals to 1. Fine. So b is not equals to 2a. The equations that you get is x1 plus x2 equals to 1. Fine. So let's plot this equation. So let's plot this. X1, this is x2. Let's choose a equals to 1 and b equals to 1. Fine. So the first equation that you get is x1 plus x2 equals to 1, right? So what is this line? You put x1, put x1 to 0, you get x2 equals to 1, right? This is 1. You put x1 equals to 0. So this is 1. So you get a line that goes like this. Fine. So this is the case when this is the first line, x1 plus x2 equals to first equation. The second equation is x1 plus x2 equals to b by 2, which is 1 by 2, right? So you will get this second line if you use this. So this is half, and you will get this. So it has no solution, right? These are parallel lines, right? So option C is true, but it is asking non-true. So option C is also correct. Fine, everyone. Do you have any doubts? Anyone do have any doubts, or if you have some confusion in the answer, then you can ask me right now. Is this clear, everyone? Am I audible? No one has any doubts? Fine. So let's start with the next problem. So I hope the way I am explaining things is clear to you, right? Should I change something? Like this is fine, right? This pattern that I am following. I am solving the problems and explaining things, what I am thinking while solving the problems. Is this fine with you guys? So which problem? This problem 3, right? So yeah, so I am basically okay, fine. So let's do this your way. So yeah, let me open up this, right, full screen, open up my rough, oh sorry, rough notes. Fine. Yeah. So let's try to do this using matrices. Fine. The question was x1 plus x2 equals to A, and then 2x1 plus 2x2 equals to B. And you want to approach this problem through linear algebra, through matrices basically, right? So you can always set up this system of matrices. So 1, 2, 1, 2, right? And then you can say x1, x2. Now this is equals to A comma B. Is this clear? Is this everyone? Have you gone through these lectures? Is this clear? Can you think of these systems of equation through this matrix vector multiplication? Fine. Now the problem is how to find solve for x1 and x2. And I believe you haven't seen this mm, inversion, basically metric inverses, right? So you won't be able to do that for solving these problems. But one thing that you can do is simply try to do Gaussian elimination to solve this system of equations. So you all know these elementary row matrix operations. Fine. So you can set up this augmented matrix you must have seen in your maybe class 12th, right? You can set up this augmented matrix system and try to get this to an identity matrix, right? So you can always say this equals to this minus this, so you will get row 2. So you can say R2, you can replace row 2 with row 2 minus row 1, and you will get 1 1 1 1 A B minus A. Fine. Now you want to set the diagonal elements to 0. And as soon as you said try to do this, any operation from here you try to do this, you will get, let's say I say R2 goes set R2 minus R1, try to do this, you will get this system of equations 1 1A, again 0 0, and B minus 2, right? So basically no single solution exists for these systems of equations. And you will see in the next week's sessions where you will learn about matrix inverses, right? So what is that depends on the matrix determinant, and you can see that you will see that the determinant of this matrix will be 0. Thus, no single solution exists for this system of equations. Fine, everyone. Do you have any doubts? Fine. Let's go back to our problem. So let's start. Which one of the following figures represent a system of linear equations with no solutions, right? So again, let's go back to our first page where we saw how to look at these problems. Fine. Screen. Yeah. So we already saw this in the first lecture, right? First problem two. So we saw geometrically what it means if your system of linear equations has unique solution, infinite many solutions, and so on, right? Fine. So if you want to find a system of equation which has no solution, you want to look at this scenario where the linear equations, the lines are parallel to each other, right? So let's go back to our problem. It says which one among the following represents a system of linear equations with no solution. Fine. So let's see. For the first, till now we were only dealing with two-dimensional space, right? So we had only two variables, x1 and x2, right? If you remember these. Now we will be dealing with system of equations in three dimensions. So these basically these slabs, these rectangular pieces that are visible on the screen are essentially planes. They are representing planes in the three-dimensional space. So for example, if you just focus here, so let's say if I draw my three-dimensional plane like this, right? And these are x, y, and z axis that we usually do on a Cartesian plane, right? So you we can always draw up a plane present in this span by these three bases, right? A linear plane. So let's say the plane passes through the origin, and so let's a simplest example would be the xy plane, right? So the xy plane basically essentially looks like this rectangular slab that lines in the xy plane, and it extends to the infinity, right? It extends to infinity. So this is an example of linear plane in the 3D space, right? Now let's say if I want to find a solution to that essentially geometrically, let's look at it in the geometric sense. So let's say if I want to find the solution to this system of equations that represent planes in 3D space, right? You are using planes in 3D, representing planes in 3D space. Fine. So how to do this? How to use solve this? So basically, let's say we have plane one, which is xy in the xy plane, and then let's choose another plane, which is let's say yx plane, zx plane, right? So this plane will go something like this, and you want to find a solution to these planes. So what you do, you find the intersection point between these two planes, right? And since now you can always say that the intersection will be this line, this line that goes through the origin, which is basically the x-axis, right? The solution, there are infinite many points that are solution to these two set of planes, which are basically the points lying on the x-axis, right? So this has infinite many solutions lying on the x-axis. So this is how you find solution to system of equations, right? In 2D plane in a 3D Cartesian space. So these basically rectangular surfaces are essentially representing these planes, right? Going extending to the infinity, right? So figure one, can you guess? Do we have a solution here? Right, everyone? Now you have an idea. So first option, let's say this is option A. Can you find a solution for this? Option A. So yeah, let no one is answering. So let me show that point for this option A. You can see this corresponding line is the solution. So it has some set of solution. So no, it has no solution. It has some solution. Similarly, for option B, you will find these points as the solution, right? Infinite many. So option C, okay. So option C contains only one single plane, right? So all the points on this plane lie has essentially represent the solution, right? So this is a solution. This has a solution. Option D, you have three planes, right? So this is plane one, this is plane two, and this one is plane 3. Fine. Can you find a single point or a line that essentially passes through all three planes? Anyone? Can you? So meanwhile, let me take out my charger. Yeah. Fine. So you can't find. So yeah, so there is no solution for these three set of planes. Fine. So yeah, for these set of linear equations, you cannot find any solution, right? So option D is the correct answer. You cannot find any solution. This is the option that has no solution. So option D is the correct answer. Fine, everyone. Do you have any doubts? Please type in the chat box. So option C, why? Okay, I will come to these questions like what is a span and other things after towards the end of this session. Fine, everyone. So basically, Dhriti, just please hang on to your problem. So just don't forget in the end. I will ask you guys to ask some questions. So in that time you can ask during that time you can ask me these questions, these additional questions. For now, someone is asking, can you explain why option C is not does have some solution, right? The question asked which among the following figures represent a system of equations with no solutions, and the question is why option C has some solution, right? So what do you mean by solution, right? What is the definition of having a solution? So solution essentially means, do you have some points that essentially lie on the given set of planes or given set of lines? So for this plane you have infinite many points that satisfies this plane equation, right? So you have some set of points that lie on the all possible planes that we are given, right? So we are given only one single plane and you have infinite number of points that lie on this plane, right? But in option D, you have three planes and there is no one single line, single point or line that lie on all of these three planes. Fine. Is this clear? Am I clear? Sudarshini had this doubt. Is this clear, Sudarshini? Great. Fine. So let's move on to the next problem, right? Anyone else, if you have any doubts, please ask by typing in the chat box. No one has any doubt, right? Fine. So let's move on to the next question. So which one of the following characterizes a consistent system of linear equations? So I hope you all remember this, right? So try to give a solution to me. So the system of equations has unique solution always. Okay. The system of equation has infinite many solution always. The system of equation has either unique solution or infinite many solutions. The system of equations have no solution always. Fine. So whenever we talk about the solution of a system or the consistency of linear equations, we essentially categorize these equations into three categories, right? That we already saw earlier in question number 2. The first category was the category of equations with one single unique solution, where you get one single point that satisfies all the linear equations. For example, this figure, this graph, right? Then second one is infinite many solutions, when both lines lie on the same line, or if you're trying to find a basically intersection between two planes in the 3D Cartesian system, you may get this kind of systems where you will get infinite many solutions. And the third one is no solution, where the lines or the planes will be parallel, so they will never intersect anywhere. right? So these are the three categories, and the question is which characterizes a consistent system of linear equations. So by consistency, what do you mean? It means has a solution, right? Has a solution. And which of all these three categories belong to this? One is having unique solution. Yes. Infinite. Yes. If you have one or infinite number of solution, you have a solution, right? So it has to be consistent. So option A is not correct. So let's say we make it a multiple choice question. So option A is correct. Yeah. If it has unique solution, it corresponds to consistent. If it has infinite, then also option C says if it has to be either unique or infinite. So option C is basically containing these two sets, right? So option C is the correct option. Option D, the system of equation having no solution. Always no. This is essentially the definition of a consistent system. It should have some points that satisfy the all the equations, right? And some by some point we mean either one which is unique or infinite. Fine, everyone. If you have any doubts, please type in the chat box. Okay, most of you answered this question correctly, right? Great. So let's move on to the next question. For a 2 by 2 skew symmetric matrix A, fine. For a 2 by 2 skew symmetric matrix A, which on the following is always true? So let's start with the definition of skew symmetric matrices, right? So what are skew symmetric matrix, right? What is a symmetric matrix? So let's say you have a matrix A, right? You have a square matrix A. So let's jump to this. So let's write the definition for a square matrix A. It is said to be skew symmetric if and only if A equals to negative of A transpose. Fine, everyone. Do you remember this definition? It has been taught in the class, in the video lectures, right? And for this, you need to know a few things. The first one is what is meaning of matrix transpose, right? What is the meaning of matrix transpose? What is a matrix transpose? And the second one is what is a square matrix, right? So the orders are reversed. First, you need to know what is a square matrix, and the second one is what is the meaning of matrix transpose, right? So yeah, let's start. What is a matrix? Matrix is a way of representing some mathematical spaces, right? And for our convenience, let's consider matrices as containing a collection of some vectors, right? So matrices can be considered as a of vectors, right? So let's say you have a what is a vector? Vector, we all know that vector is any a vector is a quantity, mathematical quantity that essentially has a magnitude as well as a direction. So essentially, if we are talking about two-dimensional vectors, it essentially contains two elements to it. So let these elements can be written as x1 and x2. So it's a vector, right? So vectors are these quantities. These have specific properties associated with these. One is their magnitude, right? And the second one is the direction. So if in the Cartesian plane, if you draw, so let's say we are dealing with only the Euclidean Cartesian plane, then you can always say if you have to represent these bases x and y, then a point x1, a vector from a vector from the origin to that point x1 comma x2 will represent a vector, right? A line, a ray, basically a ray originating from the origin to the given point x1 comma x2 will represent the vector v. which has a magnitude which is given by norm of V and the direction that this ray points to, right? For example, you can always have, let's say we have a vector 1 comma 1, so you can always have x and y. You choose these points 1 comma 1 and you go to this point. Now you have a starting origin and a point 1 comma 1. You want to draw a ray from the origin going to the point 1 comma 1, and the direction will be this direction, the direction of this arrow, and the magnitude will be square root of 2. Fine. So these are two quantities associated with vectors, and the matrices can be considered as a set of these vectors. Not necessarily set, since set needs to have unique elements. It is a combination of these vectors, right? So let's say we have some matrix that has elements a1, a2, b1, b2. Let's say these are two vectors a1, a2, b1, b2. They can be composed into a combined into a single matrix. Now let's move ahead. So every matrix has some dimensionality, right? We all know. So this is a matrix containing two rows and two columns, right? So this is a matrix of 2 comma 2. This is also usually represented using this R2 cross 2. So let's say we have a matrix A equals to this. So you can always say A belongs to R2 cross 2. Fine. Uh, there is a this is not fixed, right? You can have matrices having more dimensions, right? Let's say we can have a matrix that has some arbitrary dimension m cross n, right? Now in this category, you have classifications. If m equals to n, it is a square matrix. If m not equals to n, then it is a rectangular matrix, right? Matrix. Fine. So we are fine till here. So now we have established what is meant by a square matrix, right, everyone? So yeah, let me add a page here, right here. Fine. So now, so now we have established what is the meaning of a matrix, square matrix. Now, yeah. So yeah, that's done. Let's move on to the next problem. What is meaning of transpose of a matrix, right? Transpose of a matrix. This is again a simple operation. This is operation. So let's say you have matrix B and you want to find the transpose out of matrix B. It is represented by B subscript T, B transpose. So basically, what is B transpose? So let's say the matrix B contains the elements B11, B12, dot dot dot, B1, M cross and M rows and columns, right? And then B M1 up to Bmn, right? So let's say this is our matrix B, any arbitrary matrix B. For example, for 3 cross 3, 3 cross 2 matrix, you can always say B11, B12, B13, B21, B22, B23, right? So basically, B is a matrix whose entry, so basically whose, and we can always access the elements of this matrix using these indexes, right? So so let's say by row and column number. So the matrix value at row number, comma, column number is given by Bij. Fine, everyone. For example, for row 1, this is row 1, column 1, you have entry B11, right? For row 2, column 3, right? Row 2, column 3, you have the entry B2, comma 3. So for row I, column j, the matrix entry is Bij. Then you define B transpose at, so B transpose at I comma j equals to Bji. So this is the definition of matrix transpose. Fine. So let's define B transpose. B transpose is essentially B11, B21, dot dot dot, Bm1. Again, you go down, down, down up to B1n, right? And the last one is essentially B. What would be it? So you get this, right? Bmn, right? Bmn. So this is what a matrix transpose looks like. Now, So now we have established two definitions, what is a matrix and what are matrix transpose, right? So now let's say we have a matrix. We let's talk about the skew symmetric matrix, right? Skew symmetric matrix, right? So you can always say the definition is A equals to minus A transpose, right? Now, what is the dimensionality? Let's say if A is a matrix of M cross N dimension, then A transpose will be a matrix of dimensions N cross M that we already saw in our example, right? So if a matrix has to be a skew symmetric matrix, then A equals to minus A transpose has to be satisfied. This means it only a matrix can only be a skew symmetric if it is a square matrix, right? Square matrix. Fine. So this is the first criteria for a matrix to be skew symmetric matrix. So for our problem, if you look at our problem, we are given 2 cross 2 matrix, right? So it is a square matrix, right? Then which of the following is always true? So diagonal elements be 0, diagonal elements will be non-zero and must be the same. Diagonal elements be non-zero but different and of the same sign. Diagonal elements must be non-zero and be different and of the opposite signs. So let's do this using a simple example. So let's say we have a matrix A, B, C, D. So let's write in A transpose as A, C, B, D, right? Now I'm saying A equals to minus A transpose. This means A at row I column J is equals to minus of A transpose at row I comma column J, right? This means let's start with row 1 1. So row 1, so let's say row 1 column row call, right? 1 1. So you have A and A transpose, right? So A is A, B has entry A, right? Then 1 2 A has entry B, B has A transpose has entry C. Again 1 2 1 you have C and B, and 2 2 you have D and D. Now the problem is the thing that we want to ensure is Aij equals to minus Aij. So from first row 1 1 you can say A has to be equals to minus A, then B equals to minus C, then C equals to C equals to minus B, and then option D equals to minus D, right? And we are interested in the diagonal ones, that is we are interested in these entries. What happens to these two entries, right? Now, when you say a number is A is equals to minus A, what does this mean? There is one single number that satisfies this criteria, that is A equals to 0. No other value satisfies this. Again, D equals to minus D. This is only satisfy the value D equals to 0. Is there any other solution? No, right? So the correct solution to this problem is the diagonal elements must be 0, right? So which is always true? Option A is always true. They cannot be non-zero. No, they cannot be non-zero. Option C must be non-zero. No, it has to be 0. Again, option D says non-zero, right? Option A is correct. Fine, everyone. Do you get the reasoning how we get to these solutions, right? Knowing the definition is one thing, but understanding how you get to the definition is again important, right? Using these properties only you can define multiple properties of the matrices and vectors, and you can solve various linear systems. Fine, everyone. I hope no one has any doubts. Can we proceed to the next problem? Fine. Given A equals to 1, 2, 3. Okay, fine. So I guess I am not allowed to discuss this problem. So I can consider this, right? A equals to 1, right. So which one of these operations are not allowed? So someone is asking what is the geometric meaning of transpose of a matrix. So that will essentially need you to understand something about subspaces, spaces spanned by the vectors contained in the matrix, and essentially what a row span and column span, right? So if I think these topics are not covered during the first lectures, initial lectures. So I guess we will come to this problem, to this idea of geometric meaning of transpose of matrix in later sessions, right? So let's discuss this later when you are familiar with spans and bases, right? So for now, just think of transpose operation as this operation where uh, B transpose represented by B matrix subscript T, and the entries are related in this order. B transpose at ij equals to entry of matrix B at row j column I. Fine. Yeah. So let's move on to the next problem. Anyone do you have any doubts? I guess no one has any doubts, right? Let's move on to the next problem. Given A equals to 1, 2, 3. So given A equals to 1, 2, 3 and B equals to 1, 2, which of the missing operations, matrix operations is not defined, right? So let's take out matrices 1, 2, 3, right? And the matrix A looks like this, matrix B looks like, so basically let's just think of it like this. So everyone, do you remember how we do matrix vector product, right? Matrix product, right? So let's say you have a matrix A containing one row, one vector, which is 1, 2, 3, and matrix B containing one vector, which is 1, 2. Which of the matrix operation is not defined? So by A B transpose, whatever you are saying, right? A transpose, all these correspond to matrix vector product, matrix product, right? And I hope you remember the idea of matrix product. When you say we have a matrix A of dimensions m cross n, and the matrix B of dimensions n cross k, then you can define the definition A into B. Basically, AB, you say AB is the matrix product, right? You can always define this matrix as a matrix that has dimensionality m cross k. This is by the definition of matrix product, right, everyone? I hope everyone remembers these. So the basic criteria of matrix product is that you have a matrix on the left hand side of the multiplication operator, you have matrix on the right hand side of the matrix operator or multiplication operator. So the dimensionality, the number of rows of the matrix on left, the number of columns, right, number of columns should be equals to the number of rows of the matrix on right. So this is the basic criteria for the correct definition of a possible matrix multiplication, right? So let's look into this. So now for our case, matrix A belongs have a dimensionality of 3 cross 1, and matrix B has a dimensionality of 2 cross 1, right? So so let's look at these operations, right? So the first operation says A B transpose. So let's write this. A is basically 1, 2, 3. And again, by the definition of transpose operation that we saw in the previous problem, we can always write B transpose as let's or B is 2 cross 1, so B transpose will be of dimensionality 1 cross 2. Again, A transpose will be of dimensionality 1 cross 3. So we can always write B transpose as 1, 2 like this. It's a row vector, right? Now the number of columns in this matrix is rows in this matrix is 1, right? So is this product defined? Yeah, this is defined. And this will give you a matrix of dimensions 3 cross 2. You can always check 1 into 1, 1 into 2, 2 into 1, 2 into 2, and 3 into 1, 3 into 2. So you will get this answer 3 cross 2, right? So this is defined, right? Option A is defined. So this is not correct answer. Fine, everyone. So this is not the correct answer. Let's look at B, A transpose. Again, B, A transpose. This looks like 1, 2, and A transpose again 1, 2, 3. Now this is a matrix dimensionality 2 cross 1. This is the matrix of dimensionality 1 cross 3. The number of columns of this left hand matrix is equals to number of rows in the right hand matrix. So this is defined again. So option B is also defined. So option B is not correct answer. Let's look at A transpose B, right? A transpose B. This looks like 1, 2, 3, right? And then B is 1, 2, right? That let's define the number of, count the number of rows and columns. So you have 1 row 3 column here, you have 1 row 3 column here. The number of rows on the left is 3, number of columns on the left is 3, number of rows on the right is 1. So this is not equal, right? So this is not defined. This matrix product is not defined, right? Our question asks which of the matrix operations is not defined. So the correct answer is option C. This is not defined, right? Let's again check for the last option, A transpose, right? A transpose would be 1, 2, 3, and then again 1, 2, 3. Let's again write the number of rows here, number of columns here. Number of columns is 1, number of rows here is 1, right? These are equal. So this is defined again. So option D is also not a correct option. So option C is correct. Everyone, do you have any doubts? If you have any doubts, please type in the chat box. No one has any doubts? Can we proceed? Fine. So let's move on to the next question. Now A and B are 3 cross 3 matrices where B is a matrix containing 3 row column vectors, right? Column vectors are B1, B2, and B3. Then the product AB is equals to which of these options, right? So this is a test of matrix properties. So yeah, let me just plug in my computer. So everyone, please try to solve this problem. Yeah. Fine. So let's start with this problem. The problem says let's say we have a matrix A equals to A11, A12, A13, A21, A22, A23, A31, A32, A33. Fine. And we have a matrix B containing 3 vectors B1, B2, B3. Let's write these vectors as B11, B12, B13, B21, B22, B23, 31, B32, B33. Fine, everyone. Right. So the question is, what will the matrix product look like, right? What is the meaning of A into B, right? This is not a cross product. This is basically AB, right? So what will be the value of A into B? Everyone, do you remember the matrix multiplication algorithm? I hope so, right? So you can write it as so let me try to build so let's see. So it says A11 B11 plus A12 B12 C13, B13, right? And so on, right? You know this matrix vector products, right? So let's start with the answer, right? Let's sometimes it's good to start with the options given to try to identify which pattern is correct. But you will eventually know that this can be proven that which one is correct. So let's start with the first option, AB equals 2. But yeah, again, you will have to again prove that this is not right, right, right. So yeah, let's start in the forward way only. Let's not look into the options. Right. So let me quickly define write these multiplication operations. You all know this, right? So let me just quickly define this and factorize this for you so that you can see the proof. 2 plus 3, 3, right? Space is too small. Fine. So this is the first row of the product, right? Again, we'll now for the for second row, you will start with the second row, right? So you can always let's me use the summation term here. A2I multiplied by B1I, right? I equals to 1 to 3. Again, here you can see summation 3, this into this, A2I, B2I, right? You can always, I'm just, what I'm doing is I'm simply compressing them into this summation form. 3, 2I, B3I, right? So what it's saying I goes from 1 to 3, you are adding A to 1, A to A to I. So basically, let's say I equals to 1, put I equals to 1, then put I equals to 2, and put I equals to 3. You will essentially get the expansion of what this term looks should look like. So again, you can write this I equals to 1 to 3, A3I, B1I, summation I equals to 1 to 3, A3I, B2I, summation I 3I, B3I, right? So this is the final sum, right? Now, if you pay attention to the each column of this matrix multiplication, right, everyone? No, no, no. Someone is saying matrix B's order is wrong, but no, right? Just pay attention here. B is a matrix of dimensions 3 cross 3, right? This B1 is a vector. B1 is a vector of dimension has 3 rows, 1 column, right? Again, B2 has 3 rows, 1 column. B3 has 3 rows, 1 column. Fine. So if you stack these 3 vectors in each column of the matrix, you will get a 3 by 3 matrix, right? Is this clear, Kishore? I think there was some doubt. Yeah, right. This is clear. So now let's look at this term. Let's try to figure out a solution. Factorization. Again, if you pay attention to the first column of this product, you can see this can be written as, just correct me if I'm wrong, but you can always write this as uh, how can we write this? Let's look at the matrix vector product AB1, right? AB1. So this vector is B1, this vector is B2, this vector is B3. So let's look into the following product to get to the answer, right? how does AB1 looks like? So AB1 look like this, right? It will be a vector and it will look like summation A1I, and again B1, so 1 is fixed, BI, right? So I equals to 1, 2, 3. This will be the first entry in this vector. The second entry will be A2I, A2I, B1I, right? I goes from 1 to 3, I goes from 1 to 3, A3I, B1I, right? This is A1, AB1, right? Similarly, you can define AB2 and AB3. So I can always write ABJ. I can always write like this, and this will be equals to I equals to 1 to 3 A1I B1J. Oh, sorry, BJI, right? BJI here. BJI, then summation I equals to 1 to 3 A2I BJI, again summation I equals to 1 to 3 A3IBJI. And by this summation and why I'm using BJ here, I'm simply generalizing, right? I'm generalizing this for any B. So you can put J equals to 1, you will get this value on the left that you can see, right? These values you will get. If you put J equals to 2, then you will get AB2. Similarly, AB3 can be defined. Now you look at the product A into B. Does it look like AB1? Let's look at the first column. So it says A11 B11, right? I put I equals to 1 here, plus A12 B12, put I equals to 2 here, again plus A13 B13, put I equals to 3 here. Now the second row looks like second row, first column looks like summation I equals to 1 to 3 A2I B1I, right? Again the A3I B1I, right? A3I B1I. These are matching. So this first column can be entirely replaced with AB1, right? AB1. Again, you will find the same pattern in the second column, AB2. You will find the same pattern in third column, AB3, right? So which one of these option is correct? Anyone? Option A is correct, right? We have solved this problem. So AB is equals to AB1 plus AB1 comma AB1. First row is a first column is AB1, second column is AB2, third column is AB3, right? Now let's look onto the option B. Option B is correct. That is clearly correct. Incorrect. It is saying AB is a vector. Again, AB1 is a 3 cross 1 vector. This is 3 cross 1 vector, and again this is 3 cross 1 vector. You're adding three vectors, so it is saying AB belongs to 3 cross 1 vector, which is wrong. Sorry, yeah, which is wrong, right? Since A is 3 cross 3 and B is 3 cross 3, AP will belongs to 3 cross 3 space. You know this is by the property of matrix product. So option B is incorrect. Let's look into option C. This might look correct, but this is not, because he has already established that this is equals to AB1, AB2, AB3, and you cannot write AB1 is equals to, you cannot write all, you cannot say AB1 equals to AB1 plus AB2, right? This is not true. So this option is also incorrect. Option D, B1A, B2A, B3A. Fine. You can always say this is essentially not defined, right? B1, let's say we take one B1A, right? The dimensionality of B1 is 3 cross 1. A is of dimensionality 3 cross 3. Is this matrix product matrix multiplication defined? No. Right, everyone? So option D is also incorrect. So option A is correct. And this is a useful property that will become handy when you are doing linear algebra in your future, right? So try to understand these kind of representations. They will simplify various equations, whatever you are trying to do using linear algebra. Fine, everyone. Is this clear? Do you have any doubts? Please type in the chat box. Great. Fine. So let's move on to question number 9. Fine. Fine. Let's move on to question number 9. So let A equals to 3 comma 4 and B equals to 5 minus 6 for what value of K? A B equals to B A. So again, let's do one thing. Try to find A B. So what is the value of A into B? 3, 4 minus 2, 1, 5, 3 minus 6 and K, right? Let's write this matrix product. Again, using the trick from the previous problem, we can always write this as a matrix containing these entries, AB1, right? 3, 4 minus 2, 1. So you can see how it comes handy, right? This is a matrix vector product. Again, you can say 3, 4 minus 2, 1 and minus 6 comma K, right? So this is how you can solve this easily, right? Now this matrix product you can write as 10 plus 4, 3, 12, 27, right? Minus 10 and 3 minus 7. Then again minus 18 plus, so 4K minus 18. And then 6 to 12 plus K plus 12, right? So this is the product. This is AB. Fine. The second thing that we want it to compare with is BA. So you can always write BA as 5, 3 minus 6K. This is B and A is first row, first column, which is 3 minus 2, right? Again, 5 minus 6, 3K, 4, 1, right? 4, 1. Let's write this up. This becomes 5 3 are 15 plus 12, right? 27. Again, 3 3 are 9. So minus 2K plus 9, right? Again here 5 4 is 20 minus 6 14. So 4 0 12 plus K. So K plus 12, right? And I'm saying AB equals to BA. So whenever you say matrix, let's say we have a matrix X and a matrix Y, you want to equate them, you want to say X equals to Y. What you check? You check the elements at each row, comma column pairs. So they should be same. So basically AB at row I column J should be equals to BA at row I column J for all I equals to 1 comma 2, J equals to 1 comma 2, right? So you want to ensure that this means 27 equals to 27 row 1. So let's do this again. Let's build this table. Yeah, row column AB value, BA value, right? Mhm. Yeah, so let's write this as row, ah, yeah, row column AB, BA, right? AB, BA, row 1 column 1, AB is 27, BA is 27, these are equal, fine. Row 1 column 2, AB is 4K minus 18, BA is 14, right? Then row 2 column 1, you have minus 7 AB and minus 2K plus 9. And row 2 column 2, you have AB as K plus 12, right? And BAK plus 12. So from the first row, first column and last row, last column, you can always say these two are equal, right? So you don't need to do anything regarding these. But for the middle elements, you need to solve this equation. So this says 4K minus 18 equals to 14, right? So you can say K equals to 32 by 4 for 8 for just 32 8, right? And then the third equation says minus 2K plus 9 equals to minus 7, right? So non solar, so This says k equals to, again, this says k equals to 8. So for k equals to 8, so the answer is k equals to 8. For k equals to 8, AB equals to BA. Fine, everyone. Do you have any doubts in this problem? This was pretty straightforward problem. You just have to do matrix product and then check the entries. Anyone, do you have any doubts in this problem? Great. So let's move on to the next problem. Suppose we have two square matrices A and B of same size, then which of the following is not necessarily true? Fine. Same size. So let's say A is a matrix that has dimensions M cross M. Again, B is a matrix that has dimensions M cross M. And which of them is not necessarily true? Let's pay attention to this, which is not correct for always, right? So the first one says the expansion that we are looking at is A plus B ka whole square, right? This is essentially the matrix A plus B multiplied by the matrix A plus B. Now you can always distribute matrix multiplication over addition, right? You remember this distributive property of multiplication over addition on matrices. So this can, you can simply distribute as A plus B into A, fine, plus B into B. Now again, you can always say expand this. So this becomes A into A, and matrix A into matrix A can be represented at A square plus B into A plus here A into B plus B into B, which is B square, right? So let's look at which option is true. So this is always true, right? Always correct. Always holds. So option A, let's come back to option A later. Option B, yeah, this is exactly what we are looking at. So this always holds, right? This always holds. Then option C, again, you can always think of option C as distributive distribution. So you can always say A plus B into A plus B can be written as A into A plus B, right? So A plus B into, so A into A plus B plus B into A plus B. You can always get to this from here also. You can always get to this from here also. Take A common. So let's start factorizing. Take A common. So A plus B. Just take B common here. You will get B into A plus B, right? So option C always holds, right? This always holds. So option C always holds. Now the last option we have to check is option A. So it says A plus B or square equals to A square plus B square plus 2AB. When can we get to this, right? What is the scenario when we can get this? We can get to this if this BA is equals to AB. So we can always say this, right? If BA equals to AB, we can always say A plus B ka whole square equals to A square plus 2AB plus B square, right? We can always get to this if and only if this condition is true. Can anyone tell me, is this condition always hold, right? The question is, does this condition always hold? Anyone? Can you tell me if this condition holds always? If this is true for all set of matrices A and B, which have same dimensions? Anyone? Right. This is not always true, right? This is not always true. So there is some pair of matrices A B such that AB is not equals to BA. Fine. So yeah, this does not hold. This is not necessarily true. So option A is the correct answer that we require for this problem. Fine. Is this clear, everyone? Do you have any doubts? There are certain conditions when this holds, but this is not true always, right? So this was all for today's problems, right, everyone? Now, if you have any doubts, if you have any doubt, you can ask me, right? Now, these were the questions that I had for you guys for this session. If you have any doubts, please ask me through the chat box. Fine. So I'm here. So it is already 7:40. So I'm here for 20 more minutes. So you can ask any questions in the chat box, right? So yeah, feel free to ask any question related to any doubt related to any of the questions covered for today's session. If you have any other doubts related to the concepts that were taught that were essentially useful in solving these problems, you can also ask those doubts. Fine. Just type in the chat box. So yeah, so let me take the problems here, right? Doubts. The first one is, without calculating, can we tell AB equals to B? And no, you cannot. So you have to do the calculations. One second thing is, there are certain patterns, certain types of matrices where this is true, right? If you can, if you are able to find that pattern, then you can all directly say that this will hold. So that you can always find some pattern matrices or patterns in matrices where you can always say, for example, the identity matrix has the property that AB equals to BA. Fine. Someone is asking what is the meaning of span. So what do you mean by span, right? So span is the space that is covered by the by the quantity that for which the span is being defined. For example, when you define a line, right? Let's say, you define a line like this. So this is the XY plane, right? And you define the line x equals to y, right? So you get this line, right? That passes through the origin, makes a 45-degree angle, right? So what is the span? Meaning of span? The span is the space traversed, covered by this line, right? So for this line, its span is, for this a line, the span is all the points such that x equals to y. So for example, 0 comma 0, 1 comma 1, 2 comma 2, 1.1 comma 1.1, and so on, right? So the span is the space covered by that vector, right? So this is, you can always write this as a vector 1 comma 1, and you can take linear combination of these vectors, right? You can scale this vector, you can always scale this vector to cover as much space as possible till infinity, right? So 1 comma 1 is, let's say you have a vector 1 comma 1, you can span the space lying on this line, that is y equals to x, right? So the span is usually associated with vectors and matrices, right? So for it essentially arises from the property of vector, what space it is basically spanning, what space it can traverse. So for example, if you have a vector, you all know that if you have a vector that goes from origin to point 1 comma 1, this vector is same as the vector that goes from 1 comma 0 to, just add 1 right? So 2 comma 1, right? These two vectors are same. Basically, what is the meaning of vector? Vector, the meaning of vector is the point at the end minus point at the beginning. So the point at the end is 2.1, the point at the beginning is 1 comma 0, which is essentially 1 comma 1. So these two vectors are equivalent. So the vectors are essentially, if you translate a vector, it remains the same vector. Fine. So now what space is spanned by this vector? This vector space spans the space. You can always translate this vector to the origin, and then it spans this space y equals to x, spans the line y equals to x. Now let's say you have two vectors, right? Now let's consider two pair vectors and the combination of two vectors, right? Let's say we are considering the vectors represented by x and y axis. So let's say we are considering vectors 1 0 and 0 1. So these are the vectors, essentially these vectors, right? This is the usually I and j cap basis that you choose if you have done some vector processing in physics, right? So you are familiar with this I cap and j cap notion. So basically I cap is essentially the 1 comma 0 vector and j cap is 0 comma 1 vector, right? Now what are the points in this space, in two-dimensional space, that you can span, that you can go to using a combination of these two vectors? Can anyone tell me? So essentially, can you form go to a point 1 comma 2? Can you go to a point 3 minus 1? Can you go to a point minus 1 um, minus 100? Can you go to a point 10 comma 100? 100 comma 100. Can you go using these two vectors, using any two linear combination of vectors? By linear combination, essentially, I'm saying scaling these vectors and adding them up. That's it. Two operations. You scale the vector and add them up. That's it. So can you scale 1 comma 0 to some value, let's say 100 comma 0, and you can again scale 0 comma 1 to 0 comma 100, and then add these two to go to the point 100 comma 100, right? Everyone, are you getting this? If you add this up, you can go to the point 100 comma 100, right? So essentially what I'm taking, I'm doing scaling these two vectors and taking adding them up. This is essentially defined as a linear operation. So I'm using linear combination of these two vectors to get a point in the 2D space, right? So essentially you can span entire 2D space. You can span the entire 2D space using these two vectors, right? You can span everything in this 2D space. So that's why the span of these two vectors is essentially the Cartesian XY plane, which is contains infinite many points. So this is the definition of span. Is this clear, Dhriti? Is this clear? Are there any doubts, Dhriti? Can you? Am I audible? Someone in the chat? So I guess no one is in the meeting. Am I on level? I don't know if I'm online even. Fine. So I guess no one is in the meeting. So yeah, if you are looking at this video recording at a later stage, then you can always go through this definition, right? So that's it. If anyone has any other doubts, I guess no one is here. If no one is here, then I should. So yeah, I will again wait for a few more minutes so that if someone joins, then I will answer their queries. Otherwise, thank you all for today's session. Let's meet in the next week. So thank you everyone for joining today.